Imagine our everyday world with length, width, and height. That's 3 dimensions. We can describe any point in this space using 3 real numbers, x, y to z, which we can mathematically represent as R3. Now add time, and we get a 4-dimensional spacetime, often represented as R3 3 spatial, 1 time, or sometimes just R4 in a purely mathematical context. The idea behind 12 dimensions, often explored in theories like string theory and M theory in physics, is that there might be even more spatial dimensions beyond the 3 we readily perceive. In a 12-dimensional theory, a point in spacetime would require 12 coordinates to fully specify its location. Mathematically, a 12-dimensional space made of real numbers is represented as R12. Some theories might also include a time dimension, leading to notations like R11, 11 spatial, 1 time. Why don't we see these extra dimensions? The prevailing idea is called compactification. Imagine taking a 2D surface, like a sheet of paper, and rolling one of its dimensions into a tiny circle. From far away, it might look like a 1D line. Similarly, the extra dimensions in 12D theories are thought to be curled up into incredibly small, complex shapes, perhaps at the Planck scale, around 1.6 to 10 to 35 meters. These curled-up dimensions are so tiny that we and our instruments can't directly detect them. The geometry of these compactified spaces is crucial in these theories, as it's believed to determine the properties of the fundamental particles and forces we observe in our 4D spacetime. Heat to 2D. This is where things get more abstract and less about physical space as we know it. The concept of negative dimensions primarily arises in advanced mathematics, particularly in fields like algebraic topology and homological algebra. In these areas, the idea of dimension is generalized beyond its simple geometric meaning. Think about the usual dimensions. A point has dimension 0. A line has dimension 1. A plane has dimension 2. The dimension essentially tells you the number of independent coordinates needed to specify a point in that space. Going to negative dimensions isn't about having less than 0 spatial directions. Instead, in algebraic topology, mathematicians study spaces by associating algebraic structures, like groups, to them. The dimension can then refer to the index in these algebraic structures. For example, in a chain complex, which is a sequence of algebraic objects, the indices often correspond to dimension. A chain complex concentrated in degree 2 would have a non-zero object at index 2 and 0 objects elsewhere. Symbolically, if C is a chain complex, we might have C, 2, the 0, and C, I, the 0, for I, word to 2. This 2 doesn't describe a physical space, but rather a position within an abstract algebraic framework used to understand topological spaces. Here, I represents the imaginary unit, defined as E, Kubraut, 1. It's a fundamental concept in complex numbers which have the form APBI, where A and B are real numbers. When we talk about spaces involving I, we're dealing with complex spaces. Instead of using real numbers as coordinates, like in Rn, we use complex numbers as coordinates. A one-dimensional complex space is denoted as C, since each complex number, z codified is determined by 2 real numbers, x and y. A one-dimensional complex space C is actually equivalent to a 2-dimensional real space, R2. More generally, an n-dimensional complex space, C in n, is equivalent to a 2n-dimensional real space, R2. So, an I-dimension doesn't refer to a new, imaginary direction you can move in. Instead, it indicates that the underlying mathematical space is built using complex numbers as coordinates, which inherently doubles the number of real dimensions needed to describe it. These complex spaces are crucial in many areas of mathematics and physics, particularly in quantum mechanics, where wave functions are often complex valued. In summary, 12D, R12, or R11,1. A theoretical spacetime with 12 coordinates based on real numbers with extra spatial dimensions likely compactified at tiny scales. U2D, index in algebraic structures. Not a geometric space, but an index in abstract algebraic tools like chain complexes used in topology. I-dimension, spaces where coordinates are complex numbers, effectively doubling the underlying real dimensions compared to Rn.